All right, all. So this is going to be the last day on the generalized linear model, and of course, next week you have the first clean class exam on Wednesday. These are the readings that accompany this unit. I've also posted a supplemental reading that I by no means expect you to read, but I'm giving it to you as a resource because if you have to use the generalized linear model, and you want to know more of the guts of how the model works, this could be a good resource for you. So this is the kind of thing that you might save in a folder of readings, or if you happen to be working on a research project that involves this kind of model, look to this reading and you might get some useful information. So there's not going to be any homework this week, and instead what I've decided to do is I've posted a more detailed study guide. It's asking more specific questions than the last one that you saw. It's not intended to be completely comprehensive. I tried to ask sort of in the same family of the sorts of questions that you might expect to see on an in-class exam. It's focusing on conceptual stuff. I tried to hit as many of the major concepts as I could think of. You should use it as a guide to help your studying. So, if it reminds you of some issue that you want to review on, you can look to that. You can go back to that part of your notes. In addition, I've added a link to that study guide to a collaborative Google Doc. Anybody can edit it. So if you want to do some collaborative note-taking, go for it. I encourage you to do so. Yeah.
I just pulled the link up and there's actual study guide not in the document. Can I just copy and paste it?
Sure. That's your space. So the notes don't have to follow the study guide, but they can. But the main idea is that any of you can look and you can look to see what your peers are doing too.
Thank you.
So something, I'm going to go through the course evaluations in just a second, but a couple people mentioned in the course evaluations that one place where there's still a little bit of struggle in, or at least, is in graphing specifically. So the drill is going to focus mainly on that this week. So hopefully that'll help shore up any misunderstandings with respect to how to graph some of these models. Also, several of you mentioned that you're liking something more exercise-focused drills where you're given a problem and you can work on it and ask for help as needed. That's something that I've wanted to do all along. It's just that we've been pretty constrained on time and drill, but now the time constraints don't seem to be as much of an issue. So as much as possible, I'm going to try to make sure that we have that kind of drill. Where it makes sense, if you have to learn a new technique, sometimes we just don't have the time. But anyway, I've heard that comment as well. I promised to have the key done by yesterday. I spent time working on the study guide, and he's almost done, but not quite. So it should go up later today, but sorry about that, my bad. You'll have that available to help your studying as well. So I did go through the course evaluations. 10 of you responded. Thank you to those of you who did. It's a little bit fewer than in previous evaluations, but still useful to me. So a couple of general reflections on the course evaluations. One, I think just about everybody said that the videos were either the most useful or second most on that 1 to 7 scale. So good, I'm glad. I'm glad that's something that's that you're using and that finds some value in. We're going to continue to do that. Seven of you mentioned that you're interested in the unit on data management, and a couple of you additionally wrote some comments about how you'd like some more explicit coverage of how to not just how to manage data, but also how to munch it, get it into the format that you need, how to clean it, how to check for data integrity. And I've also had a couple conversations with some of you about how that sort of unit might be helpful. In retrospect, I think this is something that it might have been good to cover like at the very beginning in the first semester. We didn't do that, but it's something I'm thinking about. At any rate, I certainly think that there would be enough content to take up our flex days. So I'm thinking of doing a data management unit for 2 weeks, 2 whole weeks, starting directly after beginning classes again. I have some ideas of what might go in there, but anyway, it's going to take some preparation from me. So that's my plan right now. If I can get things together in enough time, that's what we're going to do. One thing that one of you mentioned, and I don't know if this is something that you all feel, but one of you mentioned how you're feeling, one reason that you feel less confident in R is that you have to Google stuff, and that things don't come fluidly. So let me give you tell you a secret. So I Google stuff all the time too. That's something that's just a universal. Professional developers, people who do this for their job, they Google stuff too. Use Stack Overflow, look at pop files all the time. Something I'm considering doing for the data management unit is doing some live coding, something like typing on a computer, and you all follow along as we try to clean some data. If and when we do that, you'll see I'm going to make mistakes all the time. I'm going to make typos. I'm going to have to Google stuff. Not just something that happens. One thing that does come from experience is that you develop more of an intuition of where the errors are likely to be, and you learn how to structure things in such a way to minimize errors. That's something that comes with experience. If you feel like you have to Google things all the time, well, we do. A few of you mentioned that you're still confused about lecture. I'll get into the quantitative ratings in just a little bit. Please, and I really mean it, if you're feeling confused, you can raise your hand in class. If you don't want to interrupt class, come see me. If I'm too intimidating, there's this role difference, so I can understand that. Seriously, talk to one of your peers, talk to Austin. It's hard for me to know where the sticking points are just from being up here. I can scan faces and look for confused faces, but I can only know what I get information about. That's one of the reasons that these evaluations are so useful. So if that's been your experience, that you're confused about stuff, really I want to know that so that I can try to address that confusion. And if that involves seeing one-on-one, or you staying on or whatever it is that you want to do, you should go do that. I want you to do that. As one of the things that are going badly, Keith mentioned, there were a couple places where there was a mismatch between drill and lecture. The generalized linear model was a pretty new unit that I designed, and so that's part of the reason that there was a lack of coordination. I'm certainly going to try to address that in the future. Sometimes stuff is just going to happen, but I've heard you, so I'm going to see what we can do about that. As for the quantitative ratings, so we've now done this 3 times. I don't know if the same people have responded each time. It's intentionally anonymous, but I'll show you what the time trends look like. So on lecture, late in the fall, there was a spike in perceived lecture clarity that is lower at this last time point. I'm not sure why that is, but it could be that this is the generalized linear model has some conceptually new stuff, so it would make sense to me that there would be a little bit more confusion. I'm hoping that things are starting to come together a bit, but that could make some sense to me. We have about the same readings on visual clarity. That's been something that's been pretty good since we started the course. In terms of pace, so the perceived pace is about the same as it's been every time I've done this. I realize that the pace is somewhat fast, and that's because I'm trying to help you develop that edge of growth, push you a little bit to extend what you think you might have been able to do. On drill, this is something that I'm pleased to see. So the perceived pace has gone down. From my perspective, we're actually covering about the same amount of material in each drill. I think part of what's happening is that you're more comfortable with R. And actually, on this rating of R confidence, that's something that supports that idea. So this is something that I'm really pleased to see, and I hope that's something that continues to develop. In terms of your overall evaluations of me, Austin, and the course, we actually see a pretty similar trend. Evaluations are going down. So I don't know what to make of that. Many of you actually said that you appreciated some of the changes that I made in response to evaluations, that of course is getting better, but you saw the numeric ratings. So I don't know if you're just sick of me. That's definitely a possibility. Maybe you're sick of the course. You know what? If my goal was to get you to like me, I would not be teaching this course. I would not be teaching it the way I'm teaching it. So if you're a little bit dissenting, well, that's too bad. But what I really care about most is what you're learning, and I think I see some evidence of that. So anyway, thank you for filling out this course evaluation. I'll ask you to do one more, maybe in about a month. And if you'll bear with me, it really would help me a lot. All right, so we've got our last day on the generalized linear model. There was one specific topic or one specific issue that I didn't have time for on Monday. So we're still going to be working with dichotomous outcomes. We've been going with this running example of trying to understand graduate student admissions. One difference in the model that we'll consider just a bit is we're working with two variables. So one is this rank variable, top rank schools, middle rank schools, bottom rank schools, and the other one is GPA. We've looked at models with both these variables separately. Now we're going to be considering them together. I mentioned back on Monday how one of the differences in the generalized linear model is that this idea of controlling for happens at the level of log odds rather than at the level of probability. So that's still going to be true. That's not going to be new today. But there's one little extra twist that happens when you're adding extra variables to a generalized linear model that I want to consider for today. So this is a plot of the relationship between GPA and admission. I've shown you this plot once before. The one extra twist that we have to do if we're adding in this extra variables, so whether these people went to a top ranked college, a middle ranked college, a bottom ranked college, is that I have to add that little extra information on this plot. We have the tools to do that, so I can color code these different points. I can then transform the text labels into numbers using, say, dummy coding. And I've now translated this problem into something that should be a little bit familiar, you can use these different variables to find the parameter estimates that maximize the likelihood, that maximize the conditional probability, the probability of observing these data given a certain hypothesis. And if you go through that process, you can find 3 different prediction lines for the relationship between GPA and admissions. One for top-ranked schools, one for mid-ranked schools, one for bottom-ranked schools. So this is a very similar process to the one that we followed with the general linear model, same school supply. This is one good way of visually representing this model is you get separate prediction lines, one for each group. Here's what it looks like if you look at this model in R. I'm going to go through the interpretation of the coefficients a little bit faster than I have previously, or I want to give you practice, figuring out what it means to have a certain coefficient, putting that into words. So if I use the exponentiation function, exp, that gives me my coefficient values in terms of odds, and specifically in terms of odds ratios. So first, considering this coefficient for GPA, the odds ratio for GPA, someone want to give a shot at describing in words what this coefficient means?
Is it an increase in 1 unit GPA increases the odds of admission 2.9 units across the levels of rank?
So the term phrase that I like is by a factor of. So one difference when we're working with odds as opposed to working with log odds is that you multiply things together. So this odds ratio tells you by what amount do you have to multiply the previous odds to get to the odds of someone with a unit larger GPA. So the turn of phrase that I like is someone with each unit increase in GPA increases the odds of admission by a factor of 2.9. One thing that's a little bit tricky in talking about odds ratios is that if you're using that word increase, if this increases the odds, that sort of implies causal relationship, and that's something that's you can't necessarily claim that. That's a matter of design. We talked about causal inference last semester and how there are certain cases where you can make that claim and certain places where you can't. As long as you get that word associated in there, I think it's okay. But that is a tricky thing in talking about odds ratios. So just to give you some specific wording, one way you can talk about this is every unit increase in GPA is associated with increases in the odds of admission by a factor of 2.9. So I'm getting the word associated in there to make it clear to the reader that it's generally not causal.
And that's across between schools?
Yeah, that's averaged across schools. So just as with the general linear model, you can sort of think about on average across the different schools when you're thinking about this odds ratio. All right. How about this coefficient for C1? Someone try to put that into words, what that might mean.
C1 represents the difference between top and middle, right?
That's right.
So, these, wait, I'm sorry.
So decrease in odds by a factor of 0.51 from top to middle rank schools.
Yeah, so one way to think about that is compared to people at top ranked schools, people who went to middle ranked schools had about half the odds of admission to graduate school. So we're comparing top ranked and middle ranked. One tricky thing is that you have to think about how the odds, by what number you have to multiply the previous odds to get to the other odds. And that number is about half.
Wait, what?
So instead of thinking about how much you have to add to the previous number or the previous level to get to the present level, so how much you have to add to top ranked schools to get to middle ranked schools, you have to think about what number you have to multiply by the previous level to the present level. Does that make sense? So yeah, one way to put words around this is compared to top ranked schools, people from middle ranked schools have about half the odds of admission.
Where I was getting confused there is, you brought up the word associated in the last example.
Yeah, I'm not sure. I guess if you want to put the word associated in here, I think this language doesn't necessarily imply causality. If you say about half the odds, this knows what caused that. But if you want to use the word associated, so going from a top ranked school to a middle ranked school is associated with about half the odds of admission. Or it decreased by a factor of half. That's another way to say it. One thing that I want to call out here is it's sometimes convenient, just like if you're dealing with mean differences, sometimes it's convenient to talk about how, by what number you have to, so sometimes it's convenient to talk about top ranked schools minus bottom ranked schools. So sometimes it's convenient to talk about the odds of top ranked schools versus the odds of middle ranked schools, or the reverse. So the odds of middle ranked schools versus the odds of top ranked schools. So sometimes it's convenient to talk about how, by what number you have to multiply top ranked schools to reach the odds of middle ranked schools. Sometimes it's convenient to talk about by what number you have to multiply middle ranked schools to reach top ranked schools. You can talk about going from top to bottom, middle, or middle to top. Does that make sense? So when we were working with the general linear model, you could just multiply that number by -1. If you want to talk about how middle ranked schools compare to top ranked schools, you can multiply it by -1, and then afterwards exponentiate it. So you do the mathematical operation before you exponentiate it. The reason I'm pointing this out is that if you're writing or making graphs, sometimes you want to present things one way, and sometimes it's more helpful for the viewer if you present it in a different way. So I'm just giving you this little mathematical trick because, well, I use it when in the staple write-up that I'm going to go through. I also use it in one of the graphs that I'm going to go through. Does that make sense? So basic idea, you do some sort of transformation like multiplying coefficient by -1, you do it before the exponentiation. So just to be very concrete about this, what this 1.97 means is compared to mid-ranked schools, people from top-ranked schools have about double the odds of admission. So I'm just reversing which one is compared to which. Before I was going from middle to top, now I'm going from top to middle, now I'm going from middle to top. Does that make sense? All right. What about this last coefficient for C2?
Compared to bottom ranked schools, or compared to top ranked schools, bottom grade schools have about a quarter or a fifth, almost a quarter chance of admission.
Yeah, absolutely. To be the most specific, you'd say odds of admission, because odds are slightly different from probability. So odds is, the probability of one thing versus the probability of another. Probability is just a probability. But yeah, that's purely nitpicky. Absolutely. Yeah, so the little words that I put around this, very similar to what you just talked about. And with this last coefficient too, I can do this little mathematical trick if I want to talk about how the odds increase if you go from bottom to top grade schools. So this number right here means compared to bottom ranked schools, people from top ranked schools have about 4 times the odds of admission.
And do you still write controlling for GPA for the last two?
To be the most correct, yes, you should be saying control over GPA, absolutely. That's actually a very good note. All right, so that's a little bit of interpretation. The last thing I want to do with this model is talk briefly about one oddity about working with logistic regression that comes up if you add extra variables to the model. To see what that oddity is, I've drawn 2 vertical lines connecting the middle ranked to top ranked schools here, and another one out at GPA equals 4. This is the distance that you from one end to the other of those vertical lines. Does anything seem a little strange about how this distance compares to the distance over at GPA equals 4? Does it seem different than when we were working with the regular general linear model?
So it's not equal because it's not linear.
It's not equal. And when we were working with the general linear model, what did it mean to have a distance between these 2 points that's different from the distance between these 2 points?
There's an interaction.
That there was an interaction, right? So whenever we were working with the general linear model, one way that we knew that there was an interaction is if the distance between 2 lines was different. That's one interpretation of an interaction, is that an interaction allows for different distances at different points. So it seems like the fact that these 2 distances are different, it indicates the presence of an interaction. But I didn't fit an interactive model, I fit an additive model. So that's a little bit weird. This interaction that I didn't fit, but that's present in this graph anyway, is called a mechanical interaction. It's an interaction that comes about as a result of the fact that we have to travel this link, this mathematical bridge between what's modeled and what we want to understand. So what I'm plotting is what we want to understand, which is the probability of admission. But remember, what's modeled isn't the probability of admission directly, it's the log odds of admission. So I'll show you what happens if you travel that mathematical bridge, the link function. So all I'm doing is I've transformed probability to log odds, or rather I'm plotting what the model tells me in terms of what's actually modeling, which is log odds. And if we're in log odds land, we are actually working with parallel lines. So if you calculate the distance at any point between two of these lines, it's the same wherever you calculate it. So this is a little quirk that of the generalized linear model. Sometimes because of this difference between what's modeled and what you want to understand, if you plot things in terms of what you want to understand, you get these mechanical interactions. So we can, in addition, allow these lines to be non-parallel. So we can add interactions between, say, GPA and the school break. That would allow these lines to be non-parallel too. Any interaction that we add here happens on top of the mechanical interaction that's already present. One way to think about why this happens, because it is a little bit weird, is that when we're in probability land, probabilities can't be less than 0 and they can't be greater than 1, right? And we saw that at different points along probability space. So when probability is at close to a half, the slope of our logistic curve is quite steep. The fact that that slope is changing means that if I push up this line a little bit, well, the probabilities are greater here. And so I'm going to reach that point at which the slope is steepest at a sooner point. There's nothing necessarily wrong about this, or bad even, about this little quirk of logistic regression. It's just kind of how the math works. But it can be important for interpretation because, for example, you could have a very large odds ratio when probabilities are small. That means that you have to multiply the previous odds by 20 in order to reach when you go from middle grade schools to say top grade schools. That may sound impressive, but if all the probabilities are really low, 0.001 multiplied by 20 is going to be 0.02, which is not that high a probability. That's one, interesting and sometimes weird feature about logistic regressions is, this fact that the change is steeper at different points in probability space. So, you don't necessarily need to do anything different per se when you're doing the modeling. But this is something to bear in mind is that depending on where you are in probability space, a certain odds ratio that looks impressive may not actually be impressive when we plot it out in probability space. Does that make sense? There's a blog post that I assigned that talks more about this kind of weird feature. I think it's short and pretty clear, and it also has links to other reading if you want to know more about this quirk. This is really all I want you to know is that you can get these mechanical interactions. The reason you get them is this fact that you have to translate what's modeled into what you want to understand. It means that odds ratios that sound very impressive might not be impressive in terms of what you want to understand. Yeah.
So we have to worry about a situation in which you have, it was an interactive model where so the coefficients were less than 0 or greater than 0, but it actually meant that it was a reversed relationship.
Yeah, so something that can never happen mechanically, it can never happen in this the additive model that you fit. But it can happen in interactive models, is when the logistic curves are going in opposite directions. So you might have a model where the logistic curve starts high and ends low, but then when you're looking at middle rank schools, it starts low and ends high. So that can never happen due to a mechanical interaction, but it can happen when you actually allow fit in an interactive model. Does that answer your question?
It was slightly different. It was basically the same function of the lines, but so like the distance from here to here, here to here is positive, but when you go up to this point on the graph, the relationship becomes negative. Yeah. At the inflection point, the relationship starts to
Yeah. Right. So that can happen in interactive models. It can't due to mechanical interactions. Whether you have to worry about it, I mean, if you're interpreting what's happening, yeah, you do have to think about it. But it's never something that you have to think about unless you fit that interactive model. So. All right. Let's talk about explicitly about graphing and writing about these models. Way back when I first, introduced the principles of good graphing, I gave you these principles. So different graphs have different goals. Everything that you put on the graph should further that goal. You should aim to graph things that are difficult to describe in text. In general, I think when you're working with logistic models, they're hard to understand unless you talk them out. They're hard to even talk about unless you talk to them. Take the perspective of your audience and show both model and curve. One thing that came up a little bit in the take-home exam was, I think there was some confusion about how to construct some of the graphs. I think part of that confusion maybe was the fact that, it's very understandable to have a desire to have a cookbook. If you have this model, here's the graph that you create. But if you're really thinking about what it is that you want to communicate, some of these models are complicated. It can be displayed in different ways, and different displays lead to different inferences. They highlight different things. Whenever you make a choice about what to put on your graph, you're going to de-emphasize some things and emphasize others. So it is sometimes possible to have a graph that shows everything, especially if your model is simple, but it's not always possible, and you always have to make choices. And that's what that first principle means, is you have to think about what it is that you want to display. And that's generally true in any graph that you create. And you'll get more practice thinking about that in drill. That's one comment I want to make, is that I don't think that there's a good cookbook for, if you're fitting this model, this is the graph that you should create. You're making choices, and whether to de-emphasize certain visual elements, or what aspect of the model you want to show. Do you want to show the coefficients? Are you plotting the raw data? Are you jittering your points? Are you adding horizontal lines as guides, to represent, say, the intercept? All these are choices. And I don't think that there's any set, given set of rules that dictate exactly what you do in each circumstance. So this is actually one of the reasons why I've emphasized being able to tie aspects of your model back to a graph, and also emphasize different ways of graphing models, different displays of models. What I'm hoping is that it gives you a bunch of different ways to think about what you could display. And it allows you to make choices to communicate the things that you need to communicate with the graphs. So that's one general comment that I have about just graphing in general. Um, so the model that I'm going to be showing you how to graph, I'm going to give you two different examples, but I don't think that these are exhaustive, and I don't pretend to have thought about all the different things that I could plot. I mean, there are usually multiple options, and it's not always clear which one is the right one. I am going to be working with this model right here that we just fit. And the reason I have some code up here is that I want you to be able to look at the code and look at the model output, and then be able to tie that back to the write-up that I give you with it. So I'm not going to go through this code in detail, but it's here for your reference as you're reviewing, how to translate this code into, say, a plot and a graph. One thing I just want to mention, I'm going to be using this little trick of reversing the coefficients so that it refers to the comparison between mid versus high versus, rather than high versus mid. So that thing that I mentioned, so that little mathematical trick of multiplying by -1 before you exponentiate. Okay, so this is the code that I use to generate the graph that I'll talk about in just a bit. It's here for your reference. A couple things that I want to point out are, one, I've used this little trick of setting the seed that's used to generate random numbers before I'm jittering my points. What this does is it makes sure that every time I run this code, I get the same jitter. It's just a little trick to use to make sure that you're making graphs that are perfectly reproducible. It's not something that you need to do, but it's something that I do when I'm jittering points or using some sort of random process to move that values. Another thing that I'm doing is it's often easier to work with factors when plotting rather than C1 and C2. So I talked before a little bit about how in certain circumstances it's easier to work with those contrast variables. In others, it's more efficient to work with factors. Graphing is often one of those cases where it makes sense to work with factors. So I create that factor variable with that first step. I also am jittering my points in a separate step. I'm just creating a new variable that says jitter. I just find it to be convenient to do that sometimes rather than using geom jitter. It doesn't really matter, but it's something that I just use.
Was that variable already a factor? The admit variable?
Admit should be 0 to 1. I believe maybe geom allows you to use factors, but I think it requires you to use 0 and 1 instead. So another note about what I'm doing here, I'm using this little trick called, so I'm using this function called theme_stat. If you're making a bunch of graphs and you want them to use the same theme, but you don't want to have to add that extra text every time, that's something you can do, say theme set. That just says, use this as the default theme for the session. The final thing that I'm doing that might be a little bit different from what you've done in the past is instead of putting the data set here in this first call to ggplot, I'm basically giving ggplot a custom data set every time. That the reason I'm doing that is it gives me a little bit more control about exactly what is being plotted at each point. And I'm using a separate data set for the predictions, those prediction lines that I'm plotting endpoints. I often find I just have more control over it. Oh, just one extra thing. If you've wondered how to save out plots, you can use ggsave. It's very handy. It can save in whatever format you want. Sometimes journalists want a specific image format. Use GGSave, it will just do whatever you want. I'm also saving this plot in a folder called plots. When we get to the data management unit, I'm going to talk more explicitly about how to manage the structure of the project so that things are nice, so that things aren't a complete mess. One of those little tricks that you can use is creating a little folder called plots, saving all your plots in that folder.
And this skill line continuous versus breaks, is that where the lines will be, like the labeled lines on the flags?
Yes, thank you for asking. So breaks controls the tick marks. Sometimes I don't like the tick marks that ggplot gives me by default. Sometimes I want to control them. Sometimes I want to put custom things over here in labels. So instead of the numbers 2, 3, 4, I might want to use the words 2, 3, 4. Well, you can do that using labels.
If you have on skill color discrete, but if you don't have a discrete area, continuous, is it skill color continuous or is it?
Yeah, it would be scale color continuous. Sometimes it's easier to work with scale color manual if you want to give it exactly the colors that you want to plot. Sometimes actually, if I really want to have very fine control over what I'm doing, I might have like 3 calls to geom, say geom line. And I tell it in those 3 calls, so I give it the subset of data I want to plot, and I tell it, make these red, make these blue. So I don't end up using the color aesthetic. Instead, if I really want to show it how to do exactly one thing, that's one way to do that. I don't often do that, it's more funky, it's easier to work with aesthetics, but I have done that when I want to control exactly what the plot is.
How do you decide what to name your types? Graphs of each type?
Yeah, the basic principle is that you should minimize acronyms. So you want to use plots or titles and labels that the reader can just know. So you want to be very communicative and take the perspective of the audience, like what if they can understand? What is it that, I often work with a scale called internal motivation, and it goes by the acronym IMS. And in my old lab, we would talk about IMS and the relationship between IMS and something else. IMS doesn't mean anything to a viewer unless they know those papers. Acronyms, they save space, but I think they do more harm than good. So my advice would be to minimize acronyms, but you also want to be conscious of the space that you're using. So sometimes, something that's too long just won't fit. So it's can be a bit of a balancing act. This is another thing that I mean when I say you should take the perspective of the audience and think about the goals of your graph, because taking the perspective of your audience will help you figure out what choices to make if you're thinking about what makes sense and what labels make sense.
So are you thinking of the graph as separate from the caption that normally comes with? Like if you have a graph, then a lot of times you have a caption where you maybe would write it out more so that your graph doesn't have lines.
The things that I use the caption for are technical details about what exactly is being plotted. Is this standard error, or is this the standard deviation? Is this 95% confidence interval? So, it might be how I process the data to get to this point. That's what I use the caption for. I like my figures to make a point on their own without the caption, and if the reader's interested, they can read the caption for more details. That's my preference. I really aim to make my figures have that immediate impact. But it can take some thought to figure out how to get there. No questions?
Does the ggSave function save the last plot that was made?
Yep. So you run this code, and then run ggsave. You can even, if you want, add a plus here, and it will run the ggsave in one step. I usually don't do that because I like to look at my plot before I save that. But it defaults to whatever it is that you just grabbed, whatever's on the, whatever that's called, the viewport.
And it'll override it. Like if you do this and you change something, and you just do the exact same as you say one, it'll override it.
That's right. So what this is going to do is it's going to look in the plots folder, and it's going to save out something called sample_1.png. Something's already there, it'll overwrite it. Other questions? If you run that code, this is what it gives you. I think I haven't done this yet, but for this lecture, I'll add the data set that I'm using so that you can run the code under it. Oh, it's something that I didn't mention, but I'm putting confidence bands in gray. So I got those by using SEFit equals true. I think you probably did that already in drill. For this plot, I wanted everything in gray rather than being color-coded. So in order to do that, when I made a call to geom ribbon, instead of saying color equals rank F, I said group equals rank F. So what that's going to do is it's going to plot separate elements for each group, but it's not going to differentiate the division. You could color code the ribbons, doesn't matter. I just found that this was a little bit easier to understand, and to already get like what's what just by looking at the lines. So I mentioned how, you're making choices when you're creating graphs, and one of the first things they have to do is about what it is that you want to communicate. So I'm showing you another of those choices that you could make. And for this graph, what I'm trying to show is how the odds ratios for GPA, top rank versus middle rank schools, the top rank versus low rank schools compared to each other. So I want to show what those odds ratios look like. Maybe put 95% confidence intervals around them. This is a different choice. If I'm showing odds ratios, I can't show points. But let's just imagine that you're interested in like what factors, among a bunch of factors that could help you get into graduate school, what seems to be most predictive in terms of odds. This is the kind of thing I was thinking about when I was thinking about this graph as answering that question. So one thing I'm doing up here is, the first thing is I have to collect those odds ratios, and they're 95% confidence intervals. So if you look at the one that starts odds_ratio, LB and UB, that's what I'm doing there, is collecting up the odds ratios for GPA into contrasts, and then they're 95% confidence intervals. And this is where that little mathematical trick that I mentioned of like reversing the sign comes into play, because I want to show this in terms of what might help you get into graduate school. Next, I make a little data frame that stores all of that. That's what I'm going to give to ggplot in order to like do this stuff. Using that theme set trick again. So what I'm going to be showing are points along with lines indicating 95% confidence intervals. And I've modified the labels a little bit, as well as the spacing of this one. I'm giving a subtitle. I'm modifying the subtitle. I try to make these more heavily commented in order to describe the logic of each step. So what I'll encourage you to do is, if you want to know more about how this works, like I said, I'll post the code in the data set so that you can look at it on your own. So this is what that plot looks like. I've added a horizontal line at 1 because for odds ratios, if the coefficient is different from 1, that means that there's a positive relationship. That's going back to this fact that these are multiplicative. So that's a significant difference if these 95% confidence intervals don't overlap with 1. One thing that jumps out, I think, from this plot is that going to a top-ranked school relative to a bottom-ranked school really helps a lot. GPA also helps you. But what this graph is sort of highlighting is a bunch of different comparisons of different things that could help you get into graduate school. And the first step that I took when thinking about this graph, of course, is trying to think about that question, well, what things, among a bunch of things that could help you get into graduate school, what's the most predictive? So, this may or may not make sense for any given graph that you create, but what I hope it highlights is that if you take a different starting point to what you want to show, that might lead to the construction of a different kind of graph. Questions? I'm not going to talk about the writing in a lot of detail. I'll let you read it on your own. One thing I want to highlight is how to report some statistics. So I think it's often useful to present selected probabilities somewhere in the text or in a table. Because probabilities are usually the main thing that you're interested in when you're dealing with generalized linear models. So I got these here. The other thing is how to report odds ratios and the relevant statistics. So you can give odds ratios along with 95% confidence intervals. I haven't done that here, but you could do that. To report chi-square, usually put what would be the numerator degrees of freedom, so the number of parameters that you're testing. It's like that first number that you would report using F, along with the number of cases. So the total number of people who contributed to this statistic. This is the general format that, at least DAPA recommends. Other disciplines have other standards, but this is the APA standard. Oh, and the last thing is, I'm using this language of associated with an odds increase by a factor of something. So that's one way to talk about what these mean. So the last thing I want to go through, and this is going to be much briefer, and before we get into this detail, I just want to say I don't expect you to be able to do these extensions that I'll talk about, but I want you to know that they're tools at your disposal. So there are like some big picture ideas that I'll highlight as I'm going through this section that I do want you to know, but being able to analyze data using these extensions, that's not something that I expect. Yeah.
So in terms of the test, you just want us to have a conceptual?
Yes. And I'll highlight specifically the things that I think are important. So let's imagine instead of just trying to understand whether people get admitted to graduate school, we want to know something about where they were admitted. So, most are R1s, research-intensive institutions have graduate programs. There are some R2s that also have them, and maybe you're breaking out Ivy League schools as well. This kind of problem like, it seems like it doesn't fit well with logistic regression, the thing that we just went through, because this is a 3-level outcome variable rather than a 2-level one. So the question might be, is there some way that we can tweak the generalized linear model to help it accommodate this kind of outcome? And as you might imagine, the reason I'm doing this at all is that the answer is yes. And the way you do that uses the same tools that I highlighted for logistic regression when we had that dichotomous outcome. So one tool is that distribution of the curve. We were working with binomial distributions just a moment ago. There are other distributions as well. Then the other tool is that mathematical bridge that translates what you want to understand to the thing that's modeled. You got those two things, and you can do a lot with the generalized linear model. So one idea that I want to convey here is that the generalized linear model is a very flexible set of tools. It works very well with dichotomous outcomes. It also works well with a whole bunch of other kinds of outcomes. And so if you know something about the generalized linear model, it can help you understand a lot of different research scenarios. You might have to do a little bit of reading, but this is a very flexible tool that you can use. So we were just working with dichotomous outcomes, like admission to graduate school, or some people look at, the predictors of death, or correct responses on some cognitive task. That all uses the binomial distribution, which has that weight function called the logit, the log-ops. And there's a way to use that link to go get from what you want to understand to what's modeled, and there's a way to use it in the reverse direction as well. It turns out that, I'm not going to go through the details, but it turns out that if you want to understand this kind of problem, there's another distribution called multinomial. Which actually ends up using the same kind of link function. Not going to go through the details, but now you know if you ever have to analyze that kind of data. At various points, when talking about the generalized linear model, I've talked about these ways in which the general linear model is simple. Well, it turns out that you can think of the general linear model as a special case of the generalized linear model. The way it's special is that the link function, it's called the identity function. What that means is that you don't have to travel any mathematical bridge. You want to understand the thing that's modeled, it's the same thing as the thing that you want to understand. There's no equivalence. Another very common kind of outcome that you might encounter when doing research is a count. So the number of new hires that a company makes. There's in ecology, often researchers are interested in species abundance, or the number of animals observed at a site, or if you're analyzing web-based data, that you might be interested in the number of clicks that a link gets versus maybe another link. All of those are count variables. Turns out that they have things that make them not great for the general linear model most of the time, but the generalized linear model handles them just fine. And there's the link for that kind of outcome is the logarithm. And that serves as that mathematical bridge that I mentioned. There are lots more of these. These are the most common. Basic idea, if you have an outcome that's not handled by the general linear model very well, the generalized linear model probably handles it just fine. All you need is a distribution and a link. The really great thing about the generalized linear model is that, and the general linear model, or at least pedagogically, is that all those different tools that we use with the general linear model also apply to the generalized linear model. But the one catch, of course, is that those little tweaks that you make all happen in the space that's modeled, not in the space of what you want to understand. So that creates that can create a tricky interpretation. And that's one thing that I encourage you to read up on if you have to do this yourself. But those basic ideas of how the link creates the separation applies to all these different other kinds of outcomes, just as they apply to dichotomous outcomes. This is one of the big picture ideas that I want you to understand. And it was true with dichotomous outcomes, it's also true with these other kinds of outcomes. So I'm not going to go through the output of one of these models in detail. I'll just put it here in case you need to use it on your own. But this is an example of an analysis of a count outcome, which results in something called Poisson regression. The output looks very, very similar to the output that you'd see for the dichotomous outcome. That's because it's the same kind of model. It's the generalized linear model. The only thing that I've changed is I'm now putting something different in that family argument. So before I was saying family equals binomial, now I'm saying family equals Poisson. It's a great thing about the generalized linear model. You just switch up the family and the link, and you can analyze a new kind of data. As with dichotomous outcomes, the catch, of course, is that if you want to interpret what's happening with the model, you have to think about the link, the mathematical bridge that you're traveling. And the type of link will dictate what you need to do in order to understand the thing that you're actually interested in. So from a big picture perspective, there are two things that can go badly when you're trying to think about these links and distributions. First is that the distribution can be wrong. Kind of makes sense. And the next is that the link can be wrong. So to give you a sense of what can go wrong with the distribution, just as with dichotomous outcomes, most of these other kinds of distributions assume that there's this relationship between the thing that you're predicting, where you are on the thing that's modeled, and the amount of error that you have. So I talked about how at very low probabilities, what that means is that you're not getting the rare event very often. Well, that's true with a lot of these different kinds of distributions. There are these terms that you don't have to know, but I put here in case you have to do one of these problems, called over-dispersion and under-dispersion. What that means is you're either getting more variability than you might expect from the distribution or less. And there are certain things that you can do to correct for over-dispersion or under-dispersion. I'm not going to talk through it in detail. You have some notes on the slides, but the terminology that you can remember is there are these quasi distributions that account for over or under distribution. So now you have some, a slide on it if you need to know about that, and you have a search term that you can Google. So of course, the other thing that can go wrong is the link. It turns out that there are multiple links that can work for a given distribution. So we've been working with the logit. in the binomial family, there's also this thing called the probit. That's just something that's generally true. There are often multiple choices that are reasonable for a given team. For the binomial family, logit is very standard. I've never seen a case where you might have to think about it differently. Sometimes you see that out there in papers. Now you know what that means. It's there are often different reasonable choices to have that mathematical bridge that gets you to the thing that you want to understand. If you ever have to work with count variables, count variables can be problematic both on the length and this problem of too much or too little error. So that's just a note that that's true. So big picture ideas about how to extend the generalized linear model. One is that you're still using these two ingredients, a link and a distribution. And there are different choices for the links and distributions that you can make. So the same ingredients that we worked with to understand dichotomous outcomes also apply to these other kinds of outcomes. But the thing that is different and that you might want to read up on is what it means to travel that mathematical bridge to reach the thing that you're actually interested in. So that's a lot of what we spent time on with dichotomous outcomes, because traveling that mathematical bridge can be hard. It can be hard to understand what it is that you're trying to, probabilities when you're working with flock odds. Well, I mean, that's true with these other kinds of distributions too. So think carefully, do some reading. That would be my advice. So, okay, one big picture idea, you need a link, you need a bridge. The other big picture idea is that those are the two things that can go wrong if you're looking at one of these problems. You could have the wrong link, and you can have the wrong error distribution. And there are various things that you can do to fix it that vary depending on the kind of problem that you're looking at. So I know that was like very quick and kind of big picture. Maybe there's a lot on this that you don't understand precisely. This is supposed to be more of a survey rather than like in depth. It's just like, hey, if you ever have a research problem that doesn't quite fit, dichotomous outcome and doesn't quite fit quantitative outcome, there are tools that you can use to approach that question. So we're trying to empower you to tackle questions that you might not otherwise. Questions? Okay, so the big picture ideas again are there are other variations of the generalized linear model. They use the same tools that we use to understand dichotomous outcomes. You need a link and a distribution. Those are the two things that can go wrong. And the big catch usually has to do with traveling that link. That's the thing that can make interpretation hard. That's the thing that often requires thought. That's all I have. So that's the end of this unit. Next week, of course, we have the first day class exam. After that, we're going to be working on, we're talking about the leadership. See you all next week.